Welcome to the lecture 12, and we will continue today considering a Poisson process, and particularly we will consider it in a simple case on the real line. So I suppose most of students who visited the lectures of random processes, they learned about Poisson process, but today we will see that the Poisson process on the real line can be characterized by the distance between the points here. So we will start with considering a Poisson point process on a half line, so on R plus from 0 to infinity, and here we can represent a Poisson process as a set of random points, and already we learned that how we can construct a Poisson point process, use just the construction of Poisson process on just we did it for arbitrary space on X. So we constructed as with the intensity measure mu. We learned that if we have a mu such that it is finite from the space X, we constructed a Poisson point process as sum of delta measures at random points, and we had a random number of these points. So we already did this, and this number of points here is has a Poisson distribution. So this already was done. So you know how we can represent a Poisson point process in arbitrary space. But today we will consider it on a half line, and the main difference of a half line with other spaces is that we have order between points, so we can consider them in increasing way. So we can enumerate them such that they are also following form. And actually, the name of process here can be understood in a very strict way, because we can get the intuition of a point process if we consider real line as the time. And here I will mark the first time of occurrence of some event. So we have some random times, and we count the number of events that occurs before time t. So here I had 0 of them, then one more, like, and so on. So I assume that lot of participants of these lectures heard about such Poisson process in such form. So we had the random times of appearance of some random event, and we count these random events. So this is why we call point processes, because initially it was as a function of the time, but later they was generalized for arbitrary spaces. So now the question is that we can characterize a Poisson point process not only by the distribution of these random points, but also if we will know the distribution between the of these intervals, the lengths of the intervals, then it turns out that the distribution of the lengths of the intervals between times can uniquely determine the distribution of a point process. And for Poisson point process. And we will start with so-called homogeneous point process. So let me write. This is very simple class of Poisson point processes. Poisson process. So this means that the distribution of such point process does not depend on shift, and this is just an intuitive explanation. And to be more precisely, we say that point process, Poisson point process, homogeneous of rate, we write of rate gamma that is great, a number that is greater than 0, if it has intensity measure that is equal to gamma times lambda plus, and here I will explain that where this lambda plus is a Lebesgue measure is measure on R plus. So we just consider Lebesgue measure on half line, and the intensity measure of a Poisson point process is just some number times Lebesgue measure on half line. So what we can say, this means that, so we know that a Poisson process have independent values on non-intersected intervals, and particularly if we consider the number of points on the interval AB that is equal to some number, we can easily say that this is equal to 1 over k factorial e to the power. And here I use that I have the intensity measure, which is Lebesgue measure. So here I just write this number gamma of b minus a with minus, and here b minus a to the power k. So this is just I write what does it mean. So as I told, now I would like to present the criteria where we will define the distribution of a Poisson, of a homogeneous Poisson point process based on the distribution of the length of intervals between random points. So let us formulate it. Theorem. Sometimes you can find it called interval theorem. Interval theorem. So let's formulate it. So let eta be a point process on R plus. So we consider it on half line. Then eta is a homogeneous Poisson process on R plus with rate gamma that is greater than 0. And here I write if and only if so here we just the Tn minus Tn minus 1 and greater than 1 are independent and exponentially distributed random variables with parameters gamma. So this is gamma this. So let me specify once more what is Tn, because I didn't write the formula for them, that precise formula. So where this is important, so I write Tn is equal to, this is by definition, infimum of such T where the value of point process of 0 t is greater or equal than n. Here such. So let me show on the picture once more. So I have a point process. I have some points. So by this formula for Tn, we can see that if I fix some n, for example, n is equal to 3, then for what t, the value of from 0 to t is greater or equal than n, than 3. So for this t, here is t such that eta of 0 t is greater or equal than 3. So I just take the infimum. So this is this point exactly T3 as a definition. So we just reorder the we just enumerate points in a point process in the increasing way. So this is T1 exactly, T2, and so on. So you just can check that this is the definition. And okay, so this is it. So now let's prove the theorem. So first of all, let us see that note that we have that Tn is less than T is the same event as eta of 0 T greater or equal than n. Indeed, we just can consider the omega from one subset. So I consider that T, for example, T3 is less or equal than some fixed T. This means that the value of a point process of this interval is bigger than 3. And vice versa, if the value of the interval from 0 to t is greater than n, this means that Tn is smaller than t. So this is equality for the event. Also, we should note that from this follows that the probability that for every n, Tn is less than infinity with probability 1. So we have the for almost for all n natural numbers. Okay, so now how we can find the distribution of these increments, the distribution of increments. So to find the distribution, of a random vector. So what do we have? T1. Here T0, I didn't write. Let me write here T0 is equal to just 0 here. So the first T1 minus 0 is just T1. And next I consider the difference, T3 minus T2, and so on, Tn minus Tn minus 1. So how we can find the joint distribution of a random vector? We will consider the expectation of a function of this vector. So we consider for a function f that, so we have here n coordinates. So I consider f that acts from r plus to the power n to r plus. So this is non-negative measurable function of n variable. And for such function, we consider its expectation of the random values, so on, Tn minus Tn. And if we will prove that this can be represented as integral with density, So let me write this as a question, that if we can represent it as integral of such form, where we have here S1, S2, and so on, Sn, where we have the density of independent exponential distributions with parameter gamma. So what is the density of exponential distribution with parameter gamma? If we have independent variables, this will be gamma to the power n exponent, and here minus gamma S1 plus S2 plus and so on plus Sn ds1 ds. So since we will try to prove this formula for arbitrary f, this will gives us that the random vector t1, t2 minus t1, and so on has this density. So from this, we can see that random vector t1, t2 minus t1, and so on, tn minus 1, has density of this form, gamma to the power n, and this means that this will prove the statement that such increments are independent and exponentially distributed. So how to prove this form? So let's try to prove this formula. And what do we know? We know that we have a Poisson point process, and we have the expectation of some function of such points. So what do we know? How to calculate the expectation of some functions of points in a point process? So we will use multidimensional Mach equation. So let me recall multidimensional. That we learned, and this was exactly for Poisson point process. So what we said, that if we have the expectation of integrals of some function, let me write here some another function, function phi, that depends on some number of points of m coordinates, let's take, and if we write here the m's factorial power of Poisson point process eta, dx1 dxm, then we can calculate, so this was integral of xm, then we can calculate this as integral, and expectation we put under the integral, but we add points to I'm sorry, I didn't write here. We have a function that depends not only on points but on a measure itself. Yes, we had such function. Then we write here the expectation of phi x1 and so on xm, and here the dependence of measure, we add points at x1 delta xm. So such a new measure. And here we write down the intensity measure, the m's power of intensity measure of a Poisson point process. Tx1, tx. So let me write here eta with intensity measure. Okay, so we will try to use this formula. So actually, I use this formula because I will have here the integral over product of the space, but for now I don't have here the integral because I just have the function of some points. So let us try to represent a function of these points in terms of integral. Let us represent f of t1, t2 minus t1, and so on, tn minus tn minus 1, in term of integral with respect to process eta. Yes, we have here the integrals with respect to factorial power. So let us first recall what is the integral, what is the form of the integral with respect to factorial power. So recall that if we have a point process of the form, here I write T I from 1 to infinity, then the integral of some function x, let me write, okay, x1, x m eta of gx1, gx m. So what is it? This is just the summation over non-equal indices Im, and here I write this random points. So here phi of ti1, ti2, and so on for our tim. So this we recall from the definition of the integral with respect to factorial power. So we have here non-equal points, and we sum with respect non-equal indices. So using this information, how I can represent, so let us start from like f from t1. So here I would like to present it with in form of the integral. So I write the integral of x dx. Here I will add something. So what is it? This is the sum of t I from 1 to infinity. What should I write here in order to have just one summand? So I write here the indicator that the measure of 0 t1 t is greater than just is equal to 0 ti. So for what I we have this equality. Let me once more draw a picture. So I have this random points, and we enumerate them t1, t2, and so on. So I consider these intervals, and only for t1 we have here this indicator is equal to 1, and others are equal to 0. So I will write that indicator eta of interval 0 ti is equal to 0. So we have that this is equal to 1 for I is equal to 1, and 0 for I is not equal to 1. So in this sum, we indeed have only one value t1. So I add it here. So I write that this indicator, that value of interval 0x is equal to 0. So I represented the value of function using the integral. So I will use this formula for make equation with this function. Yes, so my function depends on x and it depends on measure. So let's do one more step and then we just generalize it. If I have 2 points n is equal to 2, how I can represent it using the integral? Again, I will try to represent it using two integrals, a double integral. Here I will add something, and here I write the factorial power of 2, dx1, dx2. So what should I add here? I will understand now. So by the formula, I just know that at first I will write ti, tj, I, j non-equal. So this is what do I need. And now I want to add here such condition that I have only one summand, which is f of t1, t2. Yes, this is a question. So at first, I will summand only where the first coordinate is less than the second. So I add this indicator here, ti less than tj. Just because I know that these points are ordered in increasing order. And again, my larger point tj must be equal to 2. So I just select 2 points, t1, t2, and I will write the condition that the measure eta of the interval from 0 to t2. Here I do not include t2 is equal to 1. So I have only one this point. So this is using these indicators, I get exactly one summand here. And this is my aim. So I just add here these indicators. So here I will write the integral where x1 less than x2 and indicate that eta of 0x2 not including x2 is equal to 1. So this is the idea, and we can generalize it. I hope that you understand the idea. So for general, let us come back. What do we want to get? We want to get the function of such form, t1, t2 minus t1, and so on. So let us write this. Now we understand how to do this. Finally, write in general case we have that a function of points t1, t2 minus t1, and so on, tn minus t1 is equal. So I write it using the integral. So I have the values. So since I ordered points, I know that these values are from 0 to infinity. Yes, they can be arbitrary. Oh, I'm sorry, n minus 1 here. N minus 1. So I have n integrals, and like here I write the indicator that I write the function f. Here x1, x2 minus x1, so on xn minus xn minus 1. Here I write the indicator that I have ordered points x1 less than x2 less than xn, and I add the indicator that value of process eta of 0 xn is equal to n minus 1. So I have exactly n minus 1 points before xn, do not including xn. And I just integrate with respect to factorial power of point process. So this was first step, and now we can apply for it expectation. So I will just add it here, and I add it here, and now I use multivariate theorem by multivariate. I just continue that. So what do we do? This is here, here all this. This is a function. I'm sorry. I just want to mark it. So this is the function from the points and measures itself. So this is all this function. This is function phi that I I use in recalling Mach equation. So here a file that depends on points and measure itself. So let's write here with phi of x1, xn, and measure eta is equal to, okay, let's write here mu of some measure mu. So this is f of x1, x2 minus x1, and so on, xn minus 1, indicator x1, x2, xn, and here important mu of 0 xn is equal to n minus 1. So this is my function of phi. And continue here. So what does Mach equation say? That we just write the integrals. We just write integrals. And here we put the expectation inside the integral, but now let me write first in terms of function phi. Here we add delta measures at points x1 plus delta measures at point xn, and here I should write the power of intensity measure. Now intensity measure is equal to gamma times lambda plus to the power n dx1 dxn. So this is, I just recall that this is intensity measure of Poisson point process. Yes. So let us substitute here this function phi. So we have non-random parts here. So this one is non-random because it depends on fixed points. This non-random, what is random, will be just an indicator that has here random measure. So I write here integrals from 0 to infinity and times. Here, what do I have? Indicator x1 less than x2 less than so on xn. Of course, I have this function. This is non-random. x2 minus x1 and so on. xn minus xn minus 1. And here, what is very important, I write, so expectation of indicator is equal to probability. So I just write the probability that the measure, I will take it into the brackets. Delta xn of the interval 0 xn is equal to n minus 1. Now, and here, since I know that I take lambda plus is equal to Lebesgue measure, so I have just constant to the power n, and here dx1 dxn, because this is just Lebesgue measure. Okay, let us consider now this probability. Just let us not this probability, let us consider this event. What is this? So I have measure of such form, the xn of the interval 0 xn is equal to n minus 1. Let us see on the picture So I have some points and points. I add them, x1, x2, and so on. I know that they are ordered. This is important, they are ordered. These points ordered. And here I have xn. And also I have random points from the initial Poisson process. I have some random points. So now I consider all these points together because I add them. So I consider all these points together. This is my new point process together. And I know that the value of this interval xn is equal exactly n minus 1. So I have here this red points of the Poisson point process and blue points of added axis. So I have two types. So if I know that I have here exactly n minus 1, 3 is x n minus 1. So we have blue points, they are exactly 1, 2, 3, and so on, n minus 1. So this means that in these intervals, I have no red points. So this means that we have no red points. This just means that the Poisson point process from this interval 0 x n is equal to 0. I have no red points here. So this is events, and in the backward order, so these events are the same. That if Poisson point process does not have points in this interval, I have here exactly n minus 1. So now we can write down this probability because we know the probability that Poisson point process xn does not have points in some interval. What is it? So this is equal to 0. We just recalled what is this probability. So this is just the e to the power minus gamma and length of the interval xn. So I substituted here. I substitute this value to this probability. And I will continue. Maybe I write like this. I continue. This was the explanation, how I continue. Long explanation. And now I can write equality. So again, I have the integrals from 0 to infinity m times, and what do I have? Ordered points xn. I have the function f from x1, x2 minus x1, and so on, xn minus xn minus 1. And this probability, e to the power minus gamma xn, and what do we have here? Gamma to the power n, dx1, dxn. So now I suppose it's not hard to change the variables and to see. So let us change the variables in what order. S1 will be x1, s2 is equal to x2 minus x1, and so on. Sn is equal to xn minus xn minus 1. So this means that if we change the variable, we will see how we can write down xn here. Xn will be just this sum of all this s1, s2, and so on. And the region of integrations, since I have just this one, I know that they are from 0 to infinity because the difference non-negative from this. So I know this n integrals from 0 to infinity. So now I don't have this indicator. I have just f from s1, s2, and so on, sn. And here I have gamma to the power n, e to the power minus gamma, here s1 plus s2 plus and so on plus sn. ds1, dsn. And that's all. As this was our aim. This was our aim at the beginning of the proof. I just recalled that we proved this. We proved this. So from this, we can see that this random vector has this density. So these values are independent and exponentially distributed with parameter gamma. So that's all here. I suppose this proof is interesting because here we learned how to use map equation. You saw the application of this equality, and I think that this approach is quite interesting to prove that the distances between points of the Poisson point process on the real line are independent and equally distributed. But this was only the first part of the theorem. We proved that if we have a Poisson point process, then we have independent, identical distributed intervals between points. And now we can prove the direction. It's not hard, so we exactly have time for this. So now assume that that I have I have the random variables tn random variables such that they have properties from the statement. This means that tn minus tn minus 1 independent, identically distributed with exponential distribution of parameter gamma. I just write shortly and from 1 to infinity, and here t0 is equal to 0. So we assume this, and now we know this. Also assume that we have a Poisson point process eta prime is a Poisson point process homogeneous. Okay, a Poisson point process with intensity measure as you told gamma times lambda plus. So this is a homogeneous Poisson point process with intensity gamma. And for this, eta prime. We prove that eta prime, so at first it can be represented at some, let me write here, ti with primes to infinity, and this random variables t n prime minus t n minus 1 prime has the property independent identical distributed exponential with parameter gamma. So we just proved it, yes? If we take some Poisson point process, homogeneous Poisson point process with intensity gamma, then the points here has such property. So what do we proved? This means that these points, like the sequence ti, has the same distribution as the sequence ti prime. So we proved this, that they have the same distribution. Now, also we can write that the value of point process at of the some subset B is equal to sum of the indicators T n belongs to B. So you just count the number of points from subset B. So here you can see that the value of Poisson point process represented, of course, in terms of Tn. So from this follows that you can see that eta of B1, eta of B2, and so on. If I take disjoint subset B1 and so on Bm, they have the same distribution as eta prime of Bm for disjoint subsets Bi. So we have the equality of such so-called multi-dimensional finite dimensional distribution for a point processes. And here we use the theorem that we proved on the third lecture, that from this we get that 2 point processes coincide. So this means that eta indeed a Poisson point process with intensity gamma. So that's all, this end of the proof. So we saw on this lecture that we can uniquely determine a Poisson point process on the real line, use the distribution of distances between its random points. So I think this was interesting because we use Mach equation and some properties from the previous lectures. So that's all for today's lecture. Thank you for your attention. See you next time.
Thank you.